Hello again. I'm going to do the next lecture. I'm going to move past 15.2. 15.2 really just said, well, not sad, just said that we're going to look at the center of mass. Go ahead and read the section, but we're going to just look at the center of gravity for an object, because if a rigid body or something moves along, and as long as our force is concurrent through there for right now, then the whole system moves along together, right? So don't worry about 15.2 so much just yet. What we do need to worry about is 15.3, and you've definitely seen it before. This is the conservation of momentum. This is probably one of the things you hopefully remember from high school physics and college physics. And so let's say we're talking about a system of particles. This system could involve 2 billiard balls or 100 billiard balls. It could be the number of atoms inside, or molecules inside a balloon, right? It could be any number when we say a system, but let's just say the summation. The summation of our initial momentums, M initial times V initial, and our first state is going to equal the summation of that same mass, because we're keeping mass constant for now, times their final velocities. And this is just a before and after situation. Okay, I like blue better, I think. We'll set up a poll. What color do you like more? Let's make this a little bit more legible to something you've seen before. This is like saying M1 V1 initial plus M2 V2 initial is equal to M1 V1 in its final state plus M2 V2 in its final state. And I went ahead and used F's and I's there instead of 1's and 2's, just so we could keep labeling our objects 1 and 2. We could have also said mass A times the velocity of A at 1 plus mass B times the velocity of B at 1 is equal to mass A times the velocity of A at 2, and we put little commas in here, plus mass B times the velocity of B at 2. Same thing. Okay, so you'll see different notation wherever you look. And in this case, this is just saying that one object's momentum before plus the object's momentum that it collides with are going to each give them new momentums. And this will come in handy because we can do this in all directions. So we can say the mass 1 times velocity 1 in the x direction plus mass 2 times v2 in the x direction is equal to mass 1 v1 in the x direction, and then we'd want to put initial final plus mass 2 times v2 in the x direction final. We can do this for the y direction. We can do this for the z direction. We'll do examples where we do that for at least 2 directions. In this case, we had 2 particles. In all of these cases, it's 2 particles. We have one particle and two particles, and they, after they collide, remain as one particle and two particle. But they could stick together. I'll go more into collision types later, but they can definitely stick together, and we would call that an inelastic collision. Just think of two cars colliding. They usually don't bounce right off each other when they hit, going separate directions at an intersection. One's going this way, another guy is going this way, or gal, and they collide somewhere in the middle, right? They both usually move off going in this direction. You can literally see the momentum vectors adding together and then moving off together, and that's exactly what's happening. We get the momentum of one object, m1 v1, an initial, plus m2 v2 initial is equal to, go ahead and say that the masses combine because they stick together, and they're going to move off with some combined velocity. So now they share a velocity. So this is a very useful equation. It's going to come in handy multiple times. This could be also two train cars, maybe. One is moving towards another one. They're about to connect with their little hook things, and afterwards they move off together. So we'd have some L1 plus some L2 is equal to some L combined in some final state. So there we have a system where we have some object 1, some object 2, and they move off at some M1 plus M2 all times VF. Alright, there you go.